All right, I only got one, two, three, four, five students this morning. I don't know what the other. Well, I know what one other is. I don't know what the other two are. We were we were talking about how we design filters from digital filters that were originally defined as an analog filter. Okay, and we started off with a first order Butterworth. Let me share my screen. Okay. So here's our Butterworth filter, analog. Okay. This has a cutoff frequency of 318.3 hertz. Okay. So into that, we substitute our bilinear transform. There's our bilinear transform. We put it into that, and we eventually, after doing all the math, we end up with, here's our digital filter. Here's our digital filter. You're supposed to have all this in your notes. And then here's the frequency response. Here's the frequency response of our digital filter. And then we plotted the magnitude of this. I compared it with the magnitude of that. We found out, yes, they're both low pass filters, but the cutoff frequency of the digital filter did not match the cutoff frequency of the original analog filter. And I said today I will tell you how to get them to match. Okay. So that's where we begin today. Okay. So remember this equation. This is called a pre-warping equation. You need to memorize this. Okay. So what happened was the cutoff frequency, we thought we were designing was 318.3 hertz, but it ended up being less than that. So we need to start off with analog frequency, analog filter that has a higher cutoff frequency. And how much higher is determined by this equation. Okay. So warp, I think the course is omega p, is 2fs, and fs is 1500. And now omega c here is the cutoff frequency of the digital filter. So remember that was 2 pi fc over fs. So that's 2 pi times 318.3 over 1500. So that is 2 times pi times 318.3 divided by 1500. 1.333 rads. So we stick that up here, 1.333 divided by 2. And calculate it has to be in rads. Calculate in radians. So omega p becomes 3000 tan of 1.333 divided by 2. Okay. Tan, oh wait a minute, 1.333 divided by 2.6665. So we take the tan of that and multiply it by 3,000, and we get 2360 hertz. I mean, radians per second. Radians per second. One of the late commas have shown up. Okay. So that means we begin with analog frequency, not of 2000 like we did before, but we begin with an analog filter with cutoff frequency of 2360. Is everybody following me so far? So we begin with the same analog filter. So HA. This time the cutoff frequency is 2360. Okay. And so we apply the bilinear transform. We apply the bilinear transform. So HD of S becomes 2360 over S plus 2360, where S is still 3,000 times Z minus 1 over Z plus 1, which is 2360 over 3,000 Z minus 1 over Z plus 1 plus 2360. And take a snip, please, because I'm moving on to page 3. By the way, one person learned how to do this all by himself because he knew it was going to be the class today. And over the weekend, he learned how to do it all by himself. And I'm impressed. Because I told him, boss, I told him that the method's right in the book. Okay. So let me just repeat what I'm trying to do here. Okay. So I have now my pre-warped analog filter, my pre-warped. So A1, I'll call it H of AP. Okay. This is pre-warped analog filter, which is now 2360 over 3000 S minus 1 over S plus 1 plus 2360. Okay. And we do the math. So that's 2360 divided by 3000. 3 plus 1 over Z minus 1 plus 2360. Gotta be, this has to be multiplied by Z plus 1. 2360 times divided by 3000 times Z plus 1. So that's and we multiply top and bottom by this coefficient, this leading coefficient in the denominator. And give me a second, please. Okay, I'm back. So 0.7867 divided by 1.7867 0.4403 z plus 1 over z minus 0.2133 divided by 1.7867 0.1194. This is our designed. That's our design digital filter. So now we need to get the frequency response of that. How do we get the frequency response of that?
You would wherever you see G, replace that with e to the power of j omega.
Yes. So h of omega then, h of omega is 0.4403 e to the j omega plus 1 over e to the j omega minus 0.1194. Send me the magnitude of that, please. Send me the magnitude of that, please, in chat. So the magnitude of h omega. Send me the magnitude, please, in chat. Tell me something. Is anybody seriously working on this, or y'all just wasting my time?
I working on it, trying to type it in the chat. That's the thing.
All right, if that's a problem, you can send it by email.
Okay.
I just don't want to be wasting time. So I know you're working on it. So I hope other people are working on it too, rather than just sitting there waiting for somebody else to do it.
I know this coming for sure in the final.
A question like is coming. Maybe not this particular problem, because because this applies to high pass filters. This applies to band pass filters. Something using the bilinear transform is coming. That's correct. Or if we have time, there's another way of designing these filters. It's called impulse invariance. So either the bilinear transform will come, or the pulse invariance will come if we get time to cover it.
Dr. Conrad, did you see what I sent?
Hold on. Okay. Oh, Mr. Johnson. How many times have I said there is no J? There is no J in the magnitude. There is no J in the phase. How many times have I said that? I want each of you to give me $1 every time I said that. And Mr. Johnson, that's not the way we do magnitudes. How many times have we found the magnitude? Thanks for trying. I think I heard an email. Let me see if that's anybody else. Mr. Roll, very good. Good for you, Mr. Roll. All right. Please pay attention. Okay, I'm going to another slide. Oh, take this room back here. So we want the magnitude of the top. over the magnitude of the bottom. Okay. Now to a new slide. H magnitude of H omega is the magnitude of top. Cosine omega plus J sine omega plus 1 magnitude over the bottom, magnitude of cosine omega plus J sine omega minus 0.1194. So the top becomes 0.4403 square root of the sum of the real cosine omega plus 1 squared plus the sum of the imaginary part. Cosine omega minus 0.1194 all squared plus sine squared omega. And this is what we have to plot. And when we plot it, we should find out this has a cutoff frequency of 318.3 hertz. Any questions about this? Okay, let's go to our octave. Okay, and stop sharing. And let's share the entire screen. And there's my octave. And this is the software from last class. Let me remind you, showing the filter not designed properly because we didn't know about pre-warping last class. Let me show you what we had last class. And there it is. Okay. The analog is blue, and the cutoff frequency was 318. So this is I got 318.5. But if you keep playing with it, you probably can get it closer. So analog cutoff frequency is correct. At 0.701, actually, it should be 318. If you go across the 302.707, you see it's only 282.5. The red digital filter was designed using the bilinear transform without using the pre-warping equation first. Okay. So now let's put in Frings response with the pre-warping equation. So let's add this in here. Let's call it numerator 2. Numerator 2 is point. It was 0.4 before, now it's 0.4403 times square root of cosine, okay, cosine plus 1, okay, close bracket, dot square, cosine of ohm, I should say.
Dr. Cartwright, did we
Yes.
leave out the omega? Oh, okay, I see it now. Sorry.
Yeah. Thanks for noticing. I noticed it at the last minute. Plus sine of ohm, close bracket, dot hot squared. Okay. So it's the same as the last one, except the coefficient's different. It was 0.4, now it's 0.4403. But everything else is the same for the numerator. And then denominator 2. Denominator 2 is, okay, square root of cosine of ohm minus 0.1194 squared plus sine plus open sine of ohm, okay, close bracket, dot squared, and then close bracket. And that's the same as the first one, except the first one's 0.2, and the second one is 0.1194. And then, oh, I need semicolon. Okay. And then on my digital 2, digital 2 equals numerical 2 dot divide denom 2 semicolon. And now we plot all three graphs on the same graph. So we go down here and we have plot F and then my digital 2. Okay. And then in the legend, we have analog digital and then pre-warped digital. And it's that pre-warped one that should be correct. Okay. And then we say save as, save file. And then we try again. All right. What do I do wrong? I spelled it wrong. This will happen. Digital See, computers are dumb. It does exactly what you tell it to do. In the future, we're going to have computers that recognize you made an error and correct for that error. AI could pretty much do that today. All right, where was I? Okay, so I'm gonna have to do that again. And then look at my filter. And there it is. See right there, see the crossover right there? See where the digital and the analog interact? So we did the design properly. So 0.7. Yeah, 0.701, come down a little bit. 0.7. A little bit more. There it is. That's a little high, 0.7015. That should be just 0.701. And it'd be 318.3. So we accomplished our goal. We designed another digital filter, but this time we used pre-warping. And indeed, we created a digital filter that has the cutoff frequency that we desire. Notice that the digital filter is a better filter. Why? Because out here is going to zero quicker than the analog. Remember, outside the pass band, we want to be zero, and the digital filter is doing a better job of getting to zero quicker. Any questions about this, folks? Okay. All right, let's do another example. But this time, I want you to tell me what to do. Okay. So design a digital filter, a digital high pass filter. To have cutoff frequency (3,000 hertz). No, 3,000 rads per second. With a sampling frequency with a sampling frequency of 2,000 hertz. The filter is to be designed with bilinear transform. So if we're going to use the bilinear transform, that tells you right away. That tells you right away you're going to begin with the analog filter. Begin with the proper first order Butterworth high pass filter. All right, step one. Tell me what step one is.
Transfer function of the analog filter.
All right, and what is that going to be?
Would that be S squared over S squared plus the square root of 2S plus 1?
Mr. Johnson, do you not understand what first order means? First order means there's no squared in your answers. I mean, we haven't learned that. I mean, we began, that's 235. If you're talking about first order, you're talking about S. 1 over S tall plus 1. That's the low pass filter. S tall over 1 plus S tall. That's the first order filter because the highest power involved is S. So somebody try again, please.
Would it be? Oh, sorry.
Go ahead.
Would it be 1 over S over omega P plus 1? It's too big.
I just gave you the answer, actually. I just gave you the answer. We begin with HA of S is equal to S tall over S tall plus 1. I just told you that. Okay. And tall is 1 over omega C. Okay. And omega C is 3,000 rods a second. So S over S for 3,000. So this here is a transfer function. This is a transfer function of a first order low pass Butterworth. So what's wrong? What's wrong with this transfer function? What's wrong with this transfer function? But before we do that, let's do it. Let's do it. Let's find the transfer function another way. Let me remind you again, because I'm sure you've forgotten how we get transfer functions of filters, common filters. I'm sure you've forgotten. I think I may have sent this out recently. I sent out to you, site. Let me find it. I don't think it's that long ago, or did I get that many emails? I sent you a site of, what was that, last class? Yes, there it is. All right, let me share my entire screen with you now. You see my screen? You see me? You see my electrical engineering laboratory 4 screen?
Yes, sir.
Yes, sir.
I sent you this link last Wednesday, but we use this link in 410. Okay. How do we specify Butterworth filters? Remember how we specified the filter? What specified the filter? What made a Butterworth filter a Butterworth filter? What made a filter a 1 dB filter, 1 dB Chebyshev filter, a 1 dB Chebyshev filter? What made it that?
What does something do with the cutoff frequency?
No, the cutoff frequency. There's a cutoff frequency no matter what kind of filter it is. The cutoff frequency does not determine what kind of filter it is. The cutoff frequency, there has to be a cutoff frequency for any kind of filter. Because if you don't have a cutoff frequency, what are you designing? What made a Butterworth filter a Butterworth filter? I can't believe one person doesn't know this. Give me a second here, please. Please put the cameras on. Please put the cameras on. I want to see who is actually in the house. Miss Anderson, you're not in the house? Miss Anderson, nobody called you to let you know I'm checking?
Yes, I hear you, Dr. Carter. They just going to put on some better clothes because I don't look too good right now.
Yeah, but we don't mind your ugly face. We love you anyway.
Sir.
Mr. Pinto, you have a lovely ceiling. I like to see your lovely face, though. Thank you. Mr. Anderson, you went to put underpants on, eh? Well, there we go. All right. We're all here except for Miss Buchap. I know why he's absent. And Mr. Kerr. I know why he's almost always absent. Okay. All right. Thank you, folks. Okay. Let me ask my question again now. You can turn your cameras off. What makes a Butterworth filter a Butterworth filter? All right. Nobody remembers 410. I feel insulted. So really, there ain't no point in me teaching you all anything. Because you learn it long enough to pass the exam.
So I got it. I think I can remember why you say is use a Butterworth, but any more specifics, but I can't remember. I think I remember why you say to use it though.
Why do you use it? Why do you use a Butterworth?
Because it has less ripples.
Yes, that's one
something like that, or to make it the line flatter, or to make it flatter, or something like that.
Make the response flat as it goes towards DC. Yes, and which is the same thing, less ripple. The thing that determines whether something is a Butterworth or a Chevy Chef or even a filter that's not named, it's the transfer function. The transfer function determines what shape your filter has. And if you want to design to have a special shape, the transfer function has a polynomial that goes with it. For example, there are Butterworth polynomials. And let's get there. And there are Chebyshev polynomials. And there's the Chebyshev. See, Chebyshev has ripples in the passband. And each of these filters has a corresponding polynomial. There it is. All right. There it is. That's why I sent you this link. Because first, I need to move the other way. See the Butterworth? First order, 1 plus s. Second order, 1 plus the square root 2s plus s squared. Look now at the Chebyshev. First order Chebyshev, 0.5 dB ripple, 2.8628 plus s. And what do we do with these polynomials? How do we form a low pass filter with these polynomials? All right, nobody knows. Nobody has any hint of what I'm talking about. So, find the first order Butterworth normalized polynomial. What does that mean? What does normalized mean?
With a cutoff frequency of 1?
1 rad per second, yes.
Yes, 1 rad.
So the transfer function for a first order is what? H first order is 1 over s plus 1. That's the first order polynomial. That's the first order Butterworth polynomial. So 1 divided by that, this is the first order low pass filter. Butterworth. Why? Because this is a Butterworth polynomial. So how do we change this? So this has a cutoff frequency of 1 rad per second. What do we do to this to get any cutoff frequency? What do you do with this transfer function?
Wouldn't S become J omega?
No, S is always J omega. S is always J omega. That doesn't change the cutoff frequency. So that's H normalized. Where we have S, we replace it by S divided by omega C. It amazes me that y'all retain none of this from 410. Therefore, multiply top and bottom by omega C. This is omega C over S plus omega C. We did this last class. This is the transfer function we used last class. So this here is first order Butterworth low pass filter with cutoff frequency equals omega C. What do we do? What do we do with this to create a high pass filter? So this is HNLPF. Where we have S, replace it by 1 over S. So HNHPF is 1 over S plus 1. Replace S by 1 over S. So this is S over 1 plus S. So this here is a transfer function. This is the transfer function for PF4, first order, okay, Butterworth. High pass filter. With what kind of frequency? With omega C equal what?
1.
Listen. Why are you giving me answers without units? I think I pointed this out earlier.
1 rods per second, sir.
Thank you very much. I don't know what I have to do to y'all to make y'all think units. I know part of the problem is I'm not backed up by the other lecturers. But you get in trouble when you don't think units. I hope your physics lecturers at least make you do units.
Yeah, they do.
I am sad your technology lectures don't make you do units. That makes me very sad. Transfer function of first order low pass, Butterworth high pass filter with omega C equals 1 rod per second. What do we do? What do we do to this to have any cutoff frequency?
We substitute S for S over omega C.
No, we substitute S over omega C for S.
Oh, fine.
Yeah, it's the same thing we did up here for the low pass filter. Okay. So H high pass filter is S over omega C, 1 plus S over omega C equals S over S plus omega C, which is what I just gave you. And a particular example is S over S plus, what was it, 3000? That's what I just gave you. Okay. And I said to you, what's wrong with this? Don't forget what we're trying to do now. This is a sidetrack we just went on. Let me forget you the problem we were solving. Let me remind you of the problem we were solving. This is the problem we were solving. We're trying to design a digital filter, digital high pass filter that will have a color frequency of 3,000 rads a second. Or what's that? What's 3,000 rads a second? How many hertz is that? Come on, folks, I expect an answer. How many hertz is that?
Is it 477.5 hertz?
Yes, thank you. So this is 477.5 hertz. Okay. All right. So that's what we're trying to do. We're trying to design a digital filter with a color frequency of 475.5 hertz. And we're using a sampling frequency of 2,000 hertz. So what is the digital color frequency we want? What is the digital color frequency we want? This was all of this. Whoops. All of this green was an aside. That's not part of our problem. That's how we come up with the analog transfer function we want. Okay. But we did that already on page 5, just by reusing what I taught you in 235. This is what I taught you in 235. And what we just did over this page here is what we did in 410. We began with the Butterworth polynomial, or the Chebyshev polynomial. I told you nothing about Chebyshev in 235. Okay. So now let's go to our design. We want a digital filter with cutoff frequency, with digital cutoff frequency of omega equals what? 477.5 divided by what's the sampling frequency? 2,000? 2,000 times 2.5. That's what we want. That's 477.5 divided by 2,000. times 2 times pi equals 1.500 radians. Okay. So to recall, the analog filter, the beginning analog filter has transfer function equal to S over S plus 3000. Okay. And we recognize this as a first order Butterworth.
Hey, Dr. Cartwright, is
Yes?
something at the bottom of your screen? You can't see the
Oh,
bottom.
you can see that, okay. First order Butterworth high pass filter with omega C equals 3000 radians a second. I said to you, what's wrong with this? What's wrong with this filter? What's wrong with this transfer function? I already gave you an example where I told you something was wrong with that filter. I already showed you that. If you're paying close attention. Why can't we use bilinear transform on this? What will happen if we use a bilinear transform on this? Why do I suddenly have that? Oh, Mr. Higgs turned on his camera. That's what happened. Thank you. I don't have one person who can tell me what's wrong with this transfer function. Oh. So what I'm hearing is the example I did, y'all didn't understand. This is what I'm hearing. The example where I did, we got the analog magnitude response. We got the first digital filter we designed. We got that response, and we found out what? It was not adequate. It did not meet the goal. And the third filter we got, what did we do to create the third filter? That's how we begin today's lesson. What did we do to create the third filter?
Pre-warp.
We pre-warped. So the problem with this cutoff frequency is it is not pre-warped. If we use a bilinear transform on this filter, we won't get a cutoff frequency of 3,000 rads a second. The digital filter we design has to be pre-warped first. So this transfer function here, we could use it to bilinear transform. We'll get an answer, but it'll give us the wrong digital cutoff frequency, because that's the nature of bilinear transformation. That's what happens when you do bilinear transformation. It gives you a cutoff frequency that is less than what you want. I thought I made that very clear in the example we did this morning, but apparently not. I don't know what y'all be doing when I'm explaining these things, and I ask any questions, and y'all tell me no questions. So we need to pre-warp. We need to pre-warp this the cutoff frequency. And how do we do that? How do we pre-warp the cutoff frequency?
Omega will be equal to 2fs tan open bracket omega over 2 close bracket.
All right. Here's how you're not reading that properly. You're reading back to me a formula, but I'm not convinced you know what it means. The pre-warped pre-warped analog cutoff frequency equals 2fs tan omega divided by 2. What's omega? Omega C, really. The desired digital cutoff frequency. Divided by 2. Well, the omega part is just the desired digital cutoff frequency. And in today's second example, omega p is going to be 2 times 2,000, right? Didn't I say something? The sampling was 2,000?
Yes.
Yes, I did. Yes. And didn't I just work out what omega c was on page 7? Yes, I worked that out as 1.500 rads divided by 2. And I have my calculator. I have my calculator in radian mode. So I have 1.5 divided by 2 tan times 2 times 2,000. And it's now what? 3726 radians per second. So instead of using the cutoff frequency, instead of using omega c equals 3,000 rads per second, we use the pre-warped. Use the pre-warped. We call it up here omega p. Omega p equals 3726. And the pre-warp is always going to be larger than the analog, the initial analog color frequency, always larger. Okay. In other words, that term there is always larger than omega c. Okay. So now we begin with H A pre-watt equals S over S plus 3726. Okay. So now what do we do with this? So what do we do with this? What do we do with this?
Find the transfer function
Of what?
of the analog as well as the digital.
No. Here's the pre-warp analog. We don't need to find that. We already found it. We just need to find the transfer function of a digital filter. And how do we find the transfer function of digital filter? How do we define the transfer function of digital filter? So now we find H of Z. How?
Okay, do we substitute S, every S, substitute for 2, it'll be equals 2 FS, open bracket, Z minus 1, close bracket over Z plus 1.
What do we call that? What are we doing when we're doing that? What is S equals 2FS times Z minus 1 over Z plus 1? What's that called?
The bilinear transform.
Exactly. Yes. Now we find H of Z by applying the bilinear transform to HAP, to the pre-warped analog. So H of Z becomes S over S plus 3726. Evaluated at S equals 2FS, 4000, Z minus 1 over Z plus 1. So that means where you see S, put 4,000, the bilinear transform. So this becomes then 4,000 over Z minus 1 over Z plus 1 over 4,000 Z minus 1 over Z plus 1 plus 3726. Okay, so that's 4,000 Z minus 1 over 4,000 Z minus 1 plus 3726 Z plus 1. And so divide top and bottom by 4,000, Z minus 1 over Z minus 1 plus 3726 divided by 4,000. Point 9315 Z plus 1. So that becomes H of Z becomes Z minus 1 over 1.9315 Z minus 0.9315 minus 1 equals negative 0.0685. And then divide top and bottom by 1.9315 reciprocal. That's 0.5177 Z minus 1 over Z minus 0.0685 divided by 1.9315 equals 0.03546. And that's our filter. That's H of Z of our filter. That's what we're after. And once we have that, we can find H of omega. And then once we have H of omega, we get the magnitude of H of omega and compare it with magnitude of H of A, not the pre-warped, but with H of A, the unpre-warped. Because the unpre-warped is what we want, but the pre-warp is what we have to use to get what we want. And I leave it to you to plot these things. Matter of fact, that could be one last assignment, couldn't it? Yeah, so on Wednesday, I'll give you one last assignment. That will be due Monday. And then, of course, a week from Wednesday is your final exam. Before I say goodbye, any last questions? All right, I hear no last questions, so have a good day.
You too.
See you later, Doc.